So one of the things that we've learned is that, so it's very tempting from a project perspective to take advantage of things that will help us reduce our testing. Testing is a very expensive part of the project. It's a very necessary part, but it's also very expensive. And because of that, it's very tempting to want to rely on solely analysis, or maybe subscale testing, which is less expensive and less logistically complex. And so, but what we found is that the analysis has made some great strides, but it's not quite there yet to rely solely upon it. I kind of would liken it to maybe in the early 80s when computational fluid dynamics, CFD, was really coming into its own and starting to be used to develop aerodynamic database, for example, for different flying vehicles. Well, some of these analysis methods are kind of in their infancy right now. They're starting to break in to be useful to us. But what we found is that we have run into some troubles where the analysis is wrong. In some cases, it's overly conservative, or maybe we're asking the analysis to do things outside of its intended use. We're extrapolating where we don't have some of that test data. And because of that, it's affected some of our designs. For example, we have something that's called an energy modulator that basically helps us ensure that we don't apply too much load to a parachute. So when the pilot parachutes, their job is to pull the main parachutes out of their bays. And the pilot parachutes kind of get a running start. They're flying away from the vehicle. And then when they load up the main parachute, the deployment bag handles, they kind of yank it out, and there's a snatch load. And what we found is that when we got a little bit of limited data of how much that snatch load was, we wanted to understand it more. So we used some analysis techniques. And when we use those analysis techniques, then we designed this energy modulator to make sure that we didn't apply too much load within the pilot parachute itself or within the main deployment bag handles. And so we designed this energy modulator, and now we've been able to implement it and go and test it in the most stressing environments. And we found that that energy modulator is way oversized. We based that on that analysis. It's good that we oversized it. It's better to be oversized than undersized, but it's one example of where relying on just analysis isn't adequate. Our parachutes are made primarily of nylon and Kevlar, and they come in different shapes, different sizes. And when we receive that material, we do lot acceptance testing to make sure that it meets our minimum specifications. And then we take that material and we, using the drawings for the parachutes that we've come up with, those parachutes are fabricated. They're fabricated by people who have a lot of experience in that fabrication process based on decades of experience by the parachute vendor that we use. Then once those parachutes are fabricated, then we pack them into packing fixtures. The size and the shape of those packing fixtures depends on the parachute that you're talking about, but for example, the main parachute is packed into a packing fixture that is fairly irregularly shaped, and the reason it is so that it will fit in the volume that's been allocated to us in the forward bay of the capsule. And we first put the canopy, the drag surface of the parachute in, and then we use a hydraulic press to push down on it to make sure that it will fit within the volume, and then we wrap the suspension lines and the riser lines in there and we do multiple presses. Sometimes we press up to 50,000 pounds using that hydraulic press. but that whole operation is very, very tightly controlled using procedures. And those procedures have been, they were initially based on experience from previous programs, but also based on the experience that we've gained over our development testing. And so we've actually put controls in place in those procedures to make sure that we don't vary too much from what we've experienced in the past, to make sure that, for example, we don't damage the parachute materials when we're pushing on it that hard, or that that when the parachute comes out, it doesn't come out out of sequence. And then once we put that lid on the parachute fixture, then we actually put it into an autoclave where we cook it at about 190 degrees Fahrenheit. And the purpose of that is to remove any residual strain within the parachute materials, so that when we eventually take it out of that packing fixture and put it into the vehicle, it doesn't grow, because we've pushed it down so hard, it kind of wants to poof out. But in going through that autoclave process, it helps to ensure that it maintains a little bit of shape. And then once we put it into the vehicle, we put something that's called a retention system that basically holds the parachute in place until it's ready for deployment. And we call it the integration process. That integration process is also very tightly controlled by procedures. That's all performed by parachute riggers that are FAA certified. And we again, that's based on past experience from previous programs, as well as during our development testing.